Hello and welcome to our presentation about our publication titled ECP2.5D Person Localization in Traffic Scenes. It's a joint work of the Intelligent Vehicles Group at TU Delft and the Environment Perception Department of Mercedes-Benz. For an intelligent vehicle, the exact location of other traffic participants is essential, especially of vulnerable road users like pedestrians or riders. Recently, there's been great interest in 3D detection only using monocular images as input. On the one hand, cameras are still cheaper than LiDAR sensors. On the other hand, the redundancy is important from a safety perspective. Many computer vision tasks have been boosted by deep learning and appropriate datasets. Still, performance of monocular 3D detection lags behind the LiDAR methods. For instance, the widely used Kitty 3D detection benchmark is still led by LiDAR-based approaches. One reason could be the low number of pedestrians in the Kitty dataset. Last year, we already published a Eurocity persons detection dataset recorded in 12 different countries all over Europe as depicted on the right. So far, we only published images and 2D person annotations like bounding boxes and orientation information. In our work here, we augment these 2D annotations by distance information using the LiDAR measurements present for every image. Hence, we enable the utilization of the dataset for 3D localization methods. Other datasets like Kitty are annotated with three-dimensional bounding boxes. For the 3D detection problem, 9 degrees of freedom have to be estimated, namely the position, orientation, and extent of an object. One example for this group is the work of Jorgensen et al. Their image-based detection network requires a total of 26 different values as surrogate for the 3D box only using images. In contrast to 3D detection, the task of 3D localization simplifies the problem to finding the position of an object in a three-dimensional space. For instance, Monocular assumes that the projected center of the three-dimensional bounding box coincides with the center of the two-dimensional bounding box in the image. They estimate the distance of persons in real world based on their 2D skeletons as input. The final 3D position of the object results from the ray of sight through the two-dimensional bounding box center according to the distance, as depicted on the right. We adopt this assumption in our dataset to solve the 3D localization problem. In our baseline experiments, we extend a YOLO version 3 2D bounding box detector by a distance regression. Our new dataset is coined ECP2.5D. It provides 123,000 highly precise two-dimensional annotation for pedestrian and rider, extended by their corresponding distance and hereby the 3D position. LiDAR point clouds will be published as well. Kitty is the only other dataset in this field that provides unblurred images, which is beneficial for image and hybrid-based methods. Yet our dataset is 12 times the size of Kitty in respect to the annotated number of pedestrians. Furthermore, our Eurocity persons dataset features a highly diverse set of various urban scenarios recorded in multiple countries at different seasons, day and night times. To automatically generate the dataset, the goal is to get the 3D position of a two-dimensional bounding box. The bounding boxes are depicted on the top right. We utilize the distance information provided by a LiDAR sensor. We reformulate this problem as finding the set containing all corresponding LiDAR points for each person annotation, as depicted on the bottom right. The challenges hereby include the time offset between the camera and the LiDAR measurements, the ego motion of the car during the recording, background regions included in the bounding boxes, as well as occlusions and overlapping instances. Our final annotation lifting approach, which addresses these issues and we use to generate our dataset, is as follows. First, we synchronize the LiDAR and camera sensors to use the temporal closest point cloud for each camera image. Second, we compensate the ego motion of the recording vehicle for each LiDAR point. This results in a point cloud, which is, aside from dynamic objects, coherent in a world-fixed frame for the image capture time. The point cloud is depicted on the bottom left. Using the extrinsic sensor calibration, we're able to project the point cloud into the image as can be seen on the center bottom. All projected points contained in the 2D annotation create the initial set of points for each person. Since some of those points could be caused by non-person objects, we utilize the results of a semantic segmentation network to filter all non-person points. For all remaining points in the set, we calculate the height in meters, given the distance of the point and the height of the corresponding bounding box in the image. We calculate this height using the projection equation of the camera. If the calculated height does not fall within a predefined interval, the point is removed from the set. Lastly, the set of remaining points for each object is used as the input for our clustering algorithm to extract the final set of LiDAR points associated to the object. Hereby, the sets of overlapping annotations are merged and clustered jointly to prevent the assignment of one point to multiple objects. The final output is a corresponding set of LiDAR points for each image annotation as depicted on the bottom right. By using the semantic information and height constraints, we are able to remove most of those points from the initial point sets, which do not correspond to the person captured by the 2D annotation. Still, due to sensor parallax, minor errors in the calibration, or imprecise semantic information, the point set used as input for our final clustering step can still contain outliers. Furthermore, overlapping person annotations, as depicted on the right, create a challenge as due to the lack of instance information, the assignment of LiDAR points to the corresponding person is non-trivial. Therefore, we apply a k-means clustering with additional constraints. As point assignments are exclusive, meaning a point can be assigned to at most one object, we merge the point sets of overlapping person annotations to perform the clustering jointly. Hereby we set the hyperparameter k, the number of cluster, to the number of persons. In their work, Wagstaff et al. Introduced two different constraints to the algorithm. We use the cannot link point pairs to integrate the information from the LiDAR points projected into the image. Only points sharing the same objects in the image space can be assigned to the same cluster. Lastly, we also introduced several extensions to the algorithm, namely a refined cluster initialization strategy, the creation of additional clusters during a warm-up phase, and the use of an outlier class. In the following, we would like to give an example of our final uplifting approach. On the top left, we show the camera image. As stated before, we use the precise two-dimensional bounding box annotations as the basis for our approach. Those are depicted as green rectangles in the image. On the bottom, we show the corresponding ego motion compensated point cloud for the current image. We project the point cloud into the camera image as shown on the top left. The results of the semantic segmentation network, which are used to remove non-person points, can also be seen along with the camera image. The point sets for each object, which are used for the clustering step, are shown on the top right. The results of the clustering, meaning the points assigned to the person, are indicated by a red marker. These points are visualized in a point cloud on the bottom as green dots. The currently selected object is highlighted by a red rectangle in the camera image, and its corresponding point cluster is also colorized red. As we wanted to quantify the quality of our uplifting approach, we performed the following control strategy. We manually annotated the true object center in the point cloud for each person on a random subset of 90 frames. We compare the outcome of our uplifting approach with the manual annotations. If the distance delta exceeds a predefined threshold epsilon m, we mark the uplifted annotation as erroneous. For an epsilon of 35 centimeters, we report an error rate of 4.2%. We also visualize the distance delta for different object sizes on the bottom right. The identified errors were caused by sensor parallax, imprecise semantic masks, wrong clustering results, or an incorrect 2D annotation. By applying the presented uplifting approach for all annotations in a reasonable subset of ECP, we were able to enrich 136,000 2D annotations with their corresponding 3D position. This results in the ECP2.5D dataset. We show the distribution of the distance of all annotations in the dataset on the left. On the right, the calculated height of all annotations is shown. Again, we use the distance information of the uplifted annotation along with its bounding box height in the image to calculate the object height. As can be seen, the height distribution shows a dataset bias towards adults. As children and smaller persons are still of great interest for mono-based 3D methods, we manually validated all uplifted annotations which calculated object height below 1.35 m, which are closer than 40 meters. This results in our small person subset used during the evaluation.
For our localization baseline experiments using the new dataset, we also adopt the assumption that the projected 3D position coincides with the 2D bounding box center. So, apart from the bounding box, only the distance has to be estimated. Herefore, we extend the 2D detector YOLO-V3. Just a quick recap. After several pooling and upsampling layers in the neural network architecture, we get feature maps of different resolutions. There we have prior box of varying size depicted in red, and the classification and box regression is done per prior box. We adapt the detection loss for homoscedastic uncertainty estimation based on Kendall's work and similar to Krauss. Taking the log likelihood loss of the softmax and the normal distribution-based box regression, we get a total loss where the class and box loss are weighted by their corresponding uncertainty variables. These are also optimized during training. We extend YOLO by adding a parallel branch for distance regression. We decided to use a heteroscedastic uncertainty model, as the monocular distance estimation is rather ill-posed and we expect the uncertainty to vary in dependence of the context of each object. So per prior box our network regressed two values, the mean distance along the z-axis and the variance. The real distance y is modeled as a normal distribution parameterized by these two values. During training we optimized the log likelihood loss where we get the L2 distance of the ground truth distance set of our ECP2.5D dataset and the regressed distance. We compare our network with a second baseline method where we assume each person to have a fixed height of 1.68 meters. This is the mean height in our dataset. The distance then is calculated using the projection equation and the bounding box height in pixels. Here we see qualitative detection results of our extended YOLO method, the first baseline. The blue predictions are quite accurate. Here we see the LiDAR point cloud corresponding to the image. The different colors depict the clusters found by our lifting approach. Using the bounding box position and estimated distance, we can calculate the 3D position shown by the teal upright ellipsoids. The flat ellipsoids show the estimated uncertainty, which is higher, for example, for the pedestrian here in the back. The overall accuracy looks good. Also for the child here it's pretty close. Small persons are challenging as they are rare in our dataset. The results of the second baseline are only good for pedestrians that match the mean height, so for example it fails for the child here. In this example the 3D localization of our network is very good, also for the child. Maybe because it is walking right next to another person, the context might help in predicting the correct distance. In the last example, the small person is partly occluded and the distance estimate isn't that good, but interestingly at least the network estimates a relatively high uncertainty that might be caused by this challenging scene. In this table you can see the quantitative results of our baseline experiments for the pedestrian class. For 2D detection evaluation we used the log average miss rate on the reasonable subset as in the original EuroCity persons publication. Our extended YOLO method, CoinDAL2, performs slightly worse than the base model only trained for detection. The detection tasks do not profit from the additional distance estimation task in our experiments. For distance evaluation we used the relative distance error averaged over matched detections. This mean relative error on all uplifted pedestrians of ECP2.5D is 5.9 percentage points. It's 1.2 points better than for the fixed height baseline L2 fixed. This shows that the network not only relies on a fixed height assumption. This is also backed by the results for the small person subset in the right column. As small persons are rare, this is also a very challenging subset, and the mean relative error is higher with 15.7. Still, it's a lot better than the fixed height baseline with 47.1. We presented our new ECP2.5D dataset that will be made available for scientific non-commercial use. We will publish 360-degree LiDAR point clouds corresponding to the images of the original EuroCity persons dataset as well as the 2.D annotations. Doing so, we opt to facilitate advanced for monocular as well as LiDAR-based or hybrid 3D localization. Our extended YOLO V3 detector, including uncertainty estimation, serves as first baseline and outperforms the second fixed height baseline on our new dataset. In the future, the extracted point cloud clusters, the 2D extent of the bounding box and the orientation information already present in EuroCity persons could be used to automatically generate enclosing 3D bounding boxes.